So we know that R divides n minus m by proposition 2. So what do we want to show, right? We want to show that h to the n is equal to h to the m, because my map is defined as phi of x to the m is equal to h to the m, and if x to the m is equal to x to the n, then better h to the n be equal to h to the m. So i.e., we want that h to the n minus m is the identity. That is what we would need to prove that this map is well defined. Oh, however, we know that the order of h divides R. That's our assumption, that the order of h divides R. And then, so as R divides n minus m, we get that the order of h divides n minus m. Well, this gives us that, right? If the order of h divides n minus m, then n minus m is just a multiple of the order of h. Hence, h to the n minus m is equal to e as desired. All this work was just to show that the map defined as phi of x to the m, so this shows phi of x to the m being equal to h to the m is well defined. Okay, so I have a well-defined map. What else do I need to show? I need to show that it takes x to h and that it's a homomorphism. But both of these properties are proved as before. Clearly x to the 1 is equal to h to the 1. And again, you can show that phi is a homomorphism by showing phi of x to the m times x to the n is equal to phi of x to n plus m. And that's phi of x quantity n plus m. So it's phi of x to the n times phi of x to the m. Just like it was done for the infinite group. So to show, I mean, it's clear that phi of x is equal to h. To show phi is a homomorphism, we proceed as in case 1. I'm not going to repeat the calculation here. The calculation is completely identical to the calculation in case 1. Okay, with this group, with this proposition in place, we can now actually prove a classification of cyclic groups, and then in the next video I'll show you how to use this proposition in concrete examples. So for us, this is going to be proposition 5. And it tells us how many really different cyclic groups are there. That is, remember we talked about isomorphisms being sort of isomorphic groups being indistinguishable from the point of view of group theory. So it turns out that if I tell you that I have a cyclic group of order n and another cyclic group of the same order, there's no way to distinguish between these two from the point of view of group theory, because both of them are isomorphic to Z mod and Z. And similarly, if I tell you that I have two infinite groups that are cyclic, it turns out there is no way to distinguish between them either from the point of view of group theory, because both of these groups are isomorphic to Z. So that's essentially what this proposition says. Any cyclic group of infinite order is isomorphic to Z. Any cyclic group of finite order n is isomorphic to Z mod nz. All right, so let's prove this proposition. Proof. So let's first take, so let G be an infinite cyclic group generated by X. So by our proposition, proposition 4, there exists a homomorphism phi from G to Z such that, well, remember, because G is infinite, I can just choose wherever I want to send the generator. So such that, let's say, phi of X is 1. Then phi of X to the n is n. Remember here the operation is addition, so phi is surjective. What else do I need to know to show that this is an isomorphism? I already know it's a homomorphism. The hard work really here is done by proposition 4. I already know it's a homomorphism, so I just need to show it's a bijection. So I already know it's surjective, so I just need injectivity. To show that phi is injective, we can calculate the kernel. Okay, so which powers of X are sent to the identity? The identity in Z under addition is 0. So which powers of X are sent to 0? Well, there's certainly X to the 0. Any other power would be sent to 0? No, according to the definition, any other power is sent to X to the n is sent to n. So only X to the 0 is going to be sent to 0. So that's it, right? Which is the identity. So this shows phi is injective. Because a homomorphism is injective if and only if the kernel consists of just the identity. So I have homomorphism, surjective, and injective. So phi is an isomorphism. Quite amazing. Any infinite cyclic group is isomorphic to Z. And you can even notice how you construct this isomorphism. You send the generator to 1. I could have also sent the generator to -1 and get another isomorphism. But one isomorphism is enough. Okay, so now let's do the other case. Let's prove that any cyclic finite group of order n is isomorphic to Z mod nz. So now let G, same thing, be a cyclic group with the order of G being n. This in particular means that the order of X is also n. Now, what was the second part of the proposition about homomorphisms? If I have a finite cyclic group, then there is a homomorphism sending X to H as long as the order of H divides the order of this group. So I'm going to take, by proposition 4, there exists a homomorphism, just like above. Phi from G to Z mod NZ such that phi of x is 1 plus NZ. Why is that true? Because the order of 1 plus NZ divides the order of G, so divides n. In fact, it's equal to n, right? But for the existence of the homomorphism, all I need is that it divides n. The fact that it's equal to n, and not just only divides n, will actually now play a role in proving that it's not only a homomorphism, but an isomorphism. Okay. Then phi of x to the r is equal to r plus nz. So if I want to get 11 plus nz, what do I plug in here? X to the 11. If I want to get 7 plus nz, I plug in x to the 7. So I can get any element I want here. So the map is surjective. So phi is surjective. These are kinds of the easy things. The hard things in constructing maps from finite groups or finite cyclic groups is actually showing they're well defined. And this is done for us by proposition 4. The hard work is in the proof of proposition 4 to show that the map is well defined. To show that it's surjective, easy. So now we need to show injectivity. So again, we're going to compute the kernel. So for injectivity, let's compute the kernel. Compute the kernel of phi. So let x to the r be in the kernel. Then phi of x to the r is, well, phi of x. Okay, so it's phi of x to the r, but here I'm going to write it like this because the operation here is addition of congruence classes. So it's kind of awkward to write a power. I'm just going to write it like this. So, but phi of x, so this is r1 plus nz. So that's r plus nz. Okay, so what does that mean? So this is supposed to be in the kernel. So that means this is 0, right? This is just nz. So nz is equal to rnz means that n must divide r. Thus, x to the r is equal to x to nq for some q in z, right? If n divides r, then r is a multiple of q. So it's a multiple of n. So x to the r, which is x to the nq, is x to the n to the q. But what's x to the n? Well, G is a cyclic group of order n, which means the order of the generator x is also n. So this is just the identity. So we get this. So what did we show? We showed that if x to the r is an element of the kernel, then actually x to the r is the identity. So the kernel is just the identity. Hence, phi is injective. So an isomorphism. So this finishes the proof. Let me give you one really neat application of this. Example. Let's consider, say, the fifth roots of unity. Well, they consist of 1, zeta 5 squared, zeta 5 cubed, zeta 5 to the 4th, where zeta 5 is cosine 2 pi over 5 plus I sine 2 pi over 5. Look, clearly, by the way it's written, you can see that this is a cyclic group. What's the generator? Zeta 5. Everything in this group is a power of zeta 5. It's a cyclic group. What's the order? The order is 5. What does the proposition then give me? It's a cyclic group of order 5, so it's isomorphic to Z mod 5Z. U5 is isomorphic to Z mod 5Z. Different operations, yet an isomorphism. A group theorist, just looking through the lens of group theory, through a telescope of group theory, cannot tell the difference between fifth roots of unity and congruence classes mod 5. To a group theorist, it's all the same. To a ring theorist, that's different, because this uses different operation than that. But for a group theorist, there's no difference. They're isomorphic. And this isomorphism is kind of neat because, I mean, you saw how you can construct these isomorphisms, right? To take a generator, so I take zeta 5, which is a generator, and send it to 1 plus 5z. So zeta 5 squared is going to go where? Well, remember, whenever you send a generator of a cyclic group determines the homomorphism, so zeta 5 squared is going to go to twice the generator. So 2 plus 5z. And so on. Zeta 5 to the r is going to go to r plus 5z. And this is, you can sort of see also that how the operation behaves nicely. Say, suppose I take zeta 5 squared, and then I take zeta 5 to the 1. So I get that that's zeta 5 2 plus 1, right? What am I doing here? I'm really adding these numbers. So if I just look at their images, this is sent to 2 plus 5z, and this is sent to 1 plus 5z, according to this homomorphism. Where is this sent? Well, this is sent to 3 plus 5z. So you see how the operation here in Z mod 5z is reflected in adding the exponents here. And the exponents are really just added mod 5, right? Because if I try to do zeta 5 to the 4th zeta 5 cubed, so that would correspond to 4 plus 5z, and this would correspond to 3 plus 5z. So if I add these two congruence classes, right, I get 7 plus 5z, which is the same thing as 2 plus 5z. But the same thing happens here upstairs. This is sent to zeta 5 to the 7, which is the same as zeta 5 squared. So these exponents here behave exactly like congruence classes modulo 5. Except you need to multiply the zeta 5s, the powers of zeta 5, to have them behave that way, while you only add the congruence classes. This is reflected in that isomorphism. Multiplication here goes to addition there. Again, in a sense, you can think of this map from here to here as sort of being some sort of a log that is getting you the exponents from the powers of zeta 5. And of course, it is not a big stretch of imagination that zeta n, the mu n, is actually isomorphic to Z mod nz. Remember, here the operation is multiplication, while here the operation is addition.